Off the eastern coast of the Philippines, beneath waters that shimmer with tropical heat and teem with the richest marine biodiversity on Earth, there is a hole. Not a shallow depression, not a gentle slope into deeper water, a hole. A vertical wound in the floor of the Pacific Ocean that plunges downward for more than 10,000 meters, 10.5 kilometers, deeper than the cruising altitude of a commercial jetliner, deeper than the height of 25 Empire State Buildings stacked end to end, deeper than light can reach, deeper than radio waves can penetrate, deeper than any human being lived to comprehend for the vast majority of recorded history. It is called the Philippine Trench, and it is one of the deepest, least explored, and most geologically violent places on the surface of this planet. The deepest point of the Philippine Trench is known as the Emden Deep, named after the German survey vessel SMS Emden, which first measured it during an oceanographic survey in 1927. The Emden Deep reaches a depth of approximately 10,540 meters below sea level. That places it among the 5 deepest points in the global ocean, behind only the Challenger Deep in the Mariana Trench, the Horizon Deep in the Tonga Trench, and the Sirena Deep, also in the Mariana Trench. The Philippine Trench is, by this measure, the 3rd deepest trench on Earth. 10.5 kilometers of water, 10.5 kilometers of darkness and pressure, of cold and silence, of forces that would destroy any unprotected object from the surface world in a fraction of a second. And yet, if you were to ask 100 people to name the deepest places on this planet, nearly all of them would mention the Mariana Trench. Perhaps a few would recall the Tonga Trench. Almost none would name the Philippine Trench. It exists in a kind of public invisibility, a place too deep to ignore and too obscure to remember. This invisibility is not merely a matter of public awareness. It extends to science itself. The number of crewed, submersible dives to the bottom of the Philippine Trench can be counted on the fingers of one hand. The total amount of time that human instruments have spent recording data on the floor of the Emden Deep is measured in hours. The total number of biological species formerly described from the Haddle zone of this trench would fill a single page. We have better maps of the far side of the moon than we do of the bottom of the Philippine Trench. We have more detailed photographs of the surface of Mars than we do of the seafloor beneath the eastern Philippines. The 3rd deepest place on our own planet is, for most practical purposes, unknown. And here is the detail that makes the Philippine Trench unlike any other deep trench on Earth. It lies within sight of land, not hundreds of kilometers offshore like the Mariana Trench, not in the empty vastness of the South Pacific like the Tonga Trench. The Philippine Trench runs parallel to the eastern coast of the Philippine archipelago, in some places less than 100 kilometers from densely populated islands. More than 100 million people live in the Philippines. Millions of them live on islands directly above or adjacent to one of the deepest features on the planet. They fish in the waters above it. They sail across it. They feel the earthquakes it generates. They endure the typhoons that draw energy from the warm waters above its depths. The Philippine Trench is not remote. It is not hidden in the middle of an empty ocean. It is right there, just offshore, beneath the same waters where children swim and fishermen cast their nets. And it is more than 10 kilometers deep. Imagine that. Imagine standing on the beach in eastern Mindanao, looking out at the Pacific Ocean, watching the waves break against the shore, and knowing that less than a day's sail from where you stand, the ocean floor drops away into a darkness so absolute, a pressure so immense, and a silence so complete that the world you know ceases to have any meaning. The sunlight that warms your face does not reach there. The air you breathe has no equivalent there. The sounds of your world, the wind, the birds, the waves, the voices of people, none of them penetrate to the bottom of the trench. It is another world, and it is closer to you than the nearest international airport. By the end of tonight, you are going to understand why the Philippine Trench is not merely a deep place on a map, but a geological engine of extraordinary power, a biological frontier of immense significance, and a seismic hazard of terrifying potential that lies closer to a major human population than any comparable feature on Earth. You are going to understand what lives in the eternal darkness of the Emden Deep, what forces carved the trench into the Pacific floor, and why the crushing weight of water at its bottom presents challenges that exceed those of outer space. And you are going to understand why, despite its proximity to one of the most densely populated nations in the world, the Philippine Trench remains one of the great blank spaces on the map of human knowledge. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The abyss is closer than you think. Imagine for a moment that you could descend. You are sealed inside a titanium sphere, barely large enough for two people, bolted into a submersible tethered to the side of a research vessel in the Philippine Sea. The hatch closes. The ballast floods. You begin to sink. For the first 100 meters, the water is warm and luminous, a tropical blue that shimmers with the reflected light of a Philippine sun. Schools of fish dart past. The hull of the support ship recedes above you, growing smaller and greener through the viewport. At 200 meters, the blue darkens. The warmth is gone. At 500 meters, the world is twilight, a deep, cold, grey-blue void where shadows have no edges, and the only movement is the occasional flash of a bioluminescent organism pulsing past your window like a star in a private universe. At 1,000 meters, the light is gone, not fading, gone. The viewport shows nothing. You are descending through absolute darkness, and you have 9,500 meters still to go. The descent continues. The temperature drops steadily toward near freezing. The pressure increases by 1 bar for every 10 meters. At 2,000 meters, the hull bears 200 bars. At 5,500 bars, you can hear the titanium respond, not creaking exactly, but making small, barely perceptible sounds, the sound of metal adjusting to forces that most materials cannot withstand. At 8,000 meters, the pressure exceeds 800 bars. You are deeper than the average depth of the ocean, deeper than most military submarines could survive for even a fraction of a second. At 10,000 meters, you pass 1,000 bars. Every square centimeter of the hull bears the weight of a small car. And then, after more than 2 hours of continuous descent through darkness, the sonar altimeter begins to register the seafloor, rising to meet you. A flat, pale expanse of fine sediment, illuminated by the submersible's lights for the first time in the history of your species. You are there, the third deepest place on Earth, the Emden Deep. To understand the Philippine Trench, we must first understand the ocean it inhabits and the forces that shape it. The Pacific Ocean is the largest single feature on the surface of this planet. It covers approximately 165 million square kilometers, an area so vast that it exceeds the combined land area of every continent and island on Earth. If you could drain the Pacific Ocean and walk across its floor, you would traverse a landscape of staggering diversity, from vast, flat abyssal plains covered in fine sediment to towering seamounts rising kilometers above the surrounding floor. From mid-ocean ridges where new crust is being created to deep trenches where old crust is being consumed, the Pacific floor is not a featureless basin. It is a world unto itself, sculpted by the same tectonic forces that build mountains and trigger earthquakes on land. And the deepest parts of this world, the Hadal Trenches, are concentrated along the western and northern margins of the Pacific, in a belt of subduction zones that circles the ocean like a ring of geological violence. This is the Ring of Fire. The Ring of Fire is a horseshoe-shaped zone approximately 40,000 kilometers long that arcs around the Pacific Ocean from New Zealand through Tonga, the Philippines, Japan, the Aleutian Islands, and down the western coasts of North and South America. Along this belt, the oceanic plate and its smaller neighbouring plates are being forced beneath continental and other oceanic plates in the process of subduction. This process generates approximately 90% of the world's earthquakes and approximately 75% of the world's active volcanoes. The Ring of Fire is not a metaphor. It is a literal ring of geological violence that encircles the largest ocean on the planet, a continuous belt of subduction zones, volcanic arcs, and deep ocean trenches that represents the most tectonically active region on Earth. The Philippine Trench lies along the western edge of this ring, one of many deep scars in the Pacific floor where the relentless convergence of tectonic plates has carved the deepest features on the surface of the planet. The concentration of deep trenches in the western Pacific is not coincidental. The western and northern margins of the Pacific are the oldest parts of the Pacific Plate, and age matters in plate tectonics. Old oceanic crust is cold, dense, and heavy. It sinks more readily into the mantle than young, warm, buoyant crust. The western Pacific, where the oldest segments of the Pacific Plate are being subducted, hosts the deepest trenches on the planet, including the Mariana Trench, the Tonga Trench, the Philippine Trench, the Kuril-Kamchatka Trench, and the Japan Trench. The depth of these trenches is a direct consequence of the age and density of the subducting plate. Old, dense crust sinks steeply, creating narrow, deep trenches. Young, buoyant crust sinks at shallow angles, creating broader, shallower features. The Philippine Trench, fed by the relatively old Philippine Sea Plate, achieves depths exceeding 10,000 meters because the descending slab is old enough, cold enough, and dense enough to pull the trench floor to near the extreme limit of what subduction can produce. The Philippine Trench trace stretches for approximately 1,320 kilometers along the eastern margin of the Philippine archipelago, from approximately the latitude of the island of Luzon in the north to the island of Halmahera in the south. It is a crescent-shaped feature, narrow relative to its length, curving gently along the eastern coast of the Philippines like a blade held parallel to the shore. At its narrowest, the trench is approximately 30 kilometers wide. At its deepest, it reaches 10,540 meters below sea level. The trench is not merely deep. It is long, steep-walled and continuous, a sustained gash in the ocean floor that represents one of the most significant plate boundaries in the western Pacific. The depth of the Philippine Trench places it in the Hadal Zone, the deepest layer of the ocean, named after Hades, the Greek god of the underworld. The Hadal Zone begins at approximately 6,000 meters and extends to the bottom of the deepest ocean trenches. There are approximately 33 Hadal trenches and troughs identified worldwide, and together they represent less than 1% of the total ocean floor area, but they account for approximately 45% of the total depth range of the ocean. They are rare features, geographically speaking, but they represent the most extreme extension of the oceanic environment. The Philippine Trench is one of the deepest of these features, and its position adjacent to a major landmass gives it characteristics that distinguish it from more isolated trenches in the open Pacific. To grasp the scale of the Philippine Trench, consider several comparisons. The depth of the Emden Deep, approximately 10,540 meters, is roughly equivalent to the cruising altitude of a long-haul commercial aircraft. If you were seated in the window of an aeroplane at 35,000 feet, looking down at the ground far below, you would be looking across a distance roughly comparable to the distance between the surface of the Pacific and the floor of the Philippine Trench. But the comparison is misleading in one critical respect. Between the aircraft and the ground, there is thin, transparent air, exerting a pressure that decreases with altitude until, at the edge of space, it approaches zero. Between the surface of the ocean and the floor of the Philippine Trench, there is 10.5 kilometers of dense, opaque, crushing seawater, exerting a pressure that increases by approximately 1 bar for every 10 meters of descent. At the bottom of the Emden Deep, the pressure reaches approximately 1,050 bars, more than 1,000 times the atmospheric pressure at sea level, more than 15,000 pounds per square inch on every surface. Every square centimeter of any object at that depth bears a force equivalent to the weight of a small car, pressing inward from every direction, without pause. If you were to drop a heavy steel ball from the surface of the ocean directly above the Emden Deep, it would take approximately 60 minutes to reach the bottom, an hour of falling through darkness, an hour of sinking through water that grows colder, denser, and more pressurized with every passing second, an hour during which the light from the surface fades from blue to grey to black, and then continues, minute after minute, through a darkness so complete that the falling ball would be indistinguishable from the water surrounding it. Consider what the pressure at the bottom of the Philippine Trench does to matter. A standard styrofoam cup, the kind used for coffee, if attached to the exterior of a submersible and lowered to the Emden Deep, would be compressed to roughly the size of a thimble. Not crumpled, not torn. Uniformly compressed, its air pockets squeezed out of existence. The material itself densified by the surrounding pressure until it retains its original shape in miniature. Researchers have performed this demonstration many times with deep-sea instruments. The cups return to the surface as perfectly formed miniatures, shrunken souvenirs of the pressure that awaits at the bottom. The physics is simple. The implications are profound. At 1050 bars, the familiar properties of materials change. Glass can implode, metal can warp, seals can fail, electronics can malfunction. The deep ocean does not merely challenge engineering. It redefines the conditions under which engineering must operate. The effect of such pressure on biological molecules is equally dramatic. Proteins, the molecular machines that carry out virtually every function in a living cell, work because they fold into precise three-dimensional shapes. At extreme pressure, the water molecules surrounding a protein are compressed, altering the balance of forces that maintain the protein's structure. At 1000 bars, most proteins from surface organisms would be pushed into non-functional conformations. Their enzymes would cease to catalyze reactions. Their structural proteins would lose their shape. Their transport proteins would fail. The organism would be crushed, not in the macroscopic sense of being physically flattened, but in the molecular sense of having its fundamental chemistry rendered inoperative. The fact that organisms at the bottom of the Philippine Trench function normally at these pressures requires biochemical adaptations of extraordinary sophistication, adaptations that scientists are only beginning to understand. Sunlight, the energy source that powers nearly every ecosystem on the surface of the Earth, penetrates seawater to a limited depth. In the clearest tropical waters, such as those found above the Philippine Trench, sunlight can reach approximately 200 meters. Below that, it fades rapidly. By 400 meters, the world is deep twilight. By 600 meters, only the faintest, most diffuse blue glow remains. By 1000 meters, the light is gone. Completely, permanently, irreversibly gone. Below 1000 meters, the ocean is dark. Not dim, not shadowed, dark. The organisms that live below 1000 meters have never experienced sunlight. They exist in a world where the concept of day and night has no meaning, where the difference between noon and midnight is precisely zero, where the only light that exists is the cold, fleeting, purposeful glow of bioluminescence, the light produced by living organisms through chemical reactions within their own bodies. Bioluminescence is not a curiosity in the deep ocean. It is the dominant form of light. Researchers estimate that approximately 75% of all organisms in the mesopelagic and bathypelagic zones are capable of producing their own light. In the waters above the Philippine Trench, the mesopelagic zone from 200 to 1000 meters is illuminated not by the sun but by the flashes, glows, and pulses of billions of organisms communicating, hunting, fleeing, and attracting mates through self-generated light. Some use bioluminescence as a lure, dangling a glowing appendage in front of a gaping mouth to attract curious prey. Some use it as camouflage, producing light on their undersides to match the faint downwelling light from above, erasing their own silhouettes when viewed from below by predators. Some use it as a burglar alarm, emitting a bright flash when attacked, startling the predator and potentially attracting a larger predator that might drive the attacker away. The deep ocean is not a world without light. It is a world where every photon is deliberate, purposeful, and biologically produced. For most of human history, the deep ocean was assumed to be lifeless. Edward Forbes, a British naturalist writing in the 1840s, proposed the azoic hypothesis, the idea that no life could exist below approximately 550 meters. Forbes based his conclusion on dredging samples from the Aegean Sea, where the number of organisms he recovered decreased with depth. He extrapolated this trend to its logical conclusion and determined that at some depth, life would cease entirely. His hypothesis was widely accepted for decades. It was also completely wrong. In the 1850s and 1860s, telegraph cables laid across the Atlantic Ocean were retrieved for repair and found to be encrusted with living organisms at depths well below Forbes' proposed limit. The Challenger expedition of the 1870s collected living organisms from every depth it sampled. The Azoic hypothesis collapsed. The ocean was alive from top to bottom. The ocean above the Philippine Trench is divided into the same 5 vertical zones that characterize all ocean basins. The epipelagic zone, from the surface to approximately 200 meters, is the zone of sunlight and photosynthesis. The mesopelagic zone, from 200 to 1,000 meters, is the twilight zone, home to the diel vertical migration, the daily movement of billions of organisms from the deep toward the surface at dusk and back again at dawn, the largest migration of biomass on the planet. The bathypelagic zone, from 1,000 to 4,000 meters, is the midnight zone, a realm of permanent darkness, near freezing temperatures, and extreme scarcity. Food in the midnight zone arrives primarily as marine snow, the continuous, slow rain of dead organic matter sinking from the productive surface waters. Marine snow consists of fragments of dead plankton, shed mucus, fecal pellets, and other biological debris. By the time it reaches the bathypelagic zone, much of the organic content has been consumed by organisms in the zones above. The creatures of the midnight zone survive on the leftovers of leftovers, the remnants of a biological feast that has been picked over by every layer of ocean above them. Many have evolved enormous mouths and distensible stomachs, allowing them to swallow prey larger than themselves, because in the midnight zone, no meal can be wasted. The abyssopelagic zone, from 4,000 to 6,000 meters, is the abyss, where the organisms are sparse, often translucent, frequently blind, and adapted to pressures ranging from 400 to 600 bars. The abyssal plains, the vast, flat, sediment-covered expanses that make up more than 50% of the Earth's surface, lie within this zone. More than half the surface of this planet is abyssal plain, and it is among the least explored terrain in existence. And the Hadal zone, from 6,000 meters to the bottom, is the domain of the deepest trenches, the most in extreme pressures, and the most enigmatic life forms on the planet. Each of these zones has its own characteristic community of organisms, its own ecological dynamics, its own food web, its own set of adaptations to the specific combination of light, pressure, temperature, and food availability that defines it. And in the waters above the Philippine Trench, these zones are stacked one above the other, in a column of water more than 10 kilometers tall, each one darker and colder and more pressurized than the one above it, each one less explored and less understood than the last. But the Philippine Trench differs from other deep trenches in a way that has profound implications for both its biology and its significance to human civilization. It is close to land. The eastern coastline of the Philippines lies, in some places, less than 100 kilometers from the trench axis. The coastal waters of the Philippines are among the most biologically diverse in the world, forming part of the Coral Triangle, a region of tropical ocean that contains the highest diversity of coral reef species on the planet. The transition from the shallow, sunlit, species-rich waters of the Coral Triangle to the dark, pressurized, species-poor waters of the Hadal Zone occurs over a horizontal distance of less than 100 kilometers. In some places, the seafloor drops from the shallow continental shelf to Hadal depths over a distance of only a few tens of kilometers. The gradient is extreme, the transition is abrupt, and the organisms that live at each end of that gradient inhabit worlds so different from each other that they might as well be on different planets. This proximity to land also means that the Philippine Trench receives a higher input of terrestrial material than most open ocean trenches. Rivers draining the mountainous islands of the eastern Philippines carry sediment, organic matter, and, increasingly, pollutants into the coastal waters, where they are transported by currents and gravity flows toward the trench. Typhoons, which strike the Philippines with devastating frequency, generating wind speeds exceeding 250 kilometers per hour and dumping enormous quantities of rainfall, trigger landslides and flash floods that deliver massive pulses of sediment to the coastal ocean. Some of this material eventually finds its way to the trench floor, carried downward by turbidity currents, underwater avalanches of sediment-laden water that cascade down the steep walls of the trench and deposit their load at the bottom. The Philippine Trench is not isolated from the surface world the way the Mariana Trench or the Tonga Trench are. It is connected to the islands above it by a continuous flow of material, a geological conveyor belt that links the mountains of the Philippines to the deepest point of the trench, more than 10 kilometers below. The Emden Deep was first sounded in 1927 by the German survey vessel SMS Emden during a scientific cruise through the Western Pacific. The measurement techniques available at that time were primitive by modern standards, relying on weighted sounding lines and early echo sounding equipment. But the depths recorded were extraordinary, confirming the existence of one of the deepest trenches in the Pacific. The discovery was significant. It demonstrated that the Western Pacific floor was not a uniform, gradually deepening basin, but a landscape punctuated by extreme features, narrow chasms that plunged to depths far greater than the average ocean floor. The Emden's measurements placed the Philippine Trench among the deepest features on the planet, a distinction that subsequent surveys would confirm and refine. Later surveys, using increasingly sophisticated multi-beam sonar technology, refined the depth measurements and revealed the trench's detailed morphology, its steep walls, its narrow floor, its asymmetric cross-section, with the landward wall typically steeper and more rugged than the seaward wall. The landward wall, the wall that faces the Philippine Islands, is sculpted by the overriding plate and shows evidence of faulting, slumping, and the scars of submarine landslides. The seaward wall, formed by the descending Philippine sea plate, is smoother but marked by the bending and cracking that occurs as the plate flexes downward into the trench. The cross-sectional profile of the trench is not symmetrical. It is V-shaped in some segments, U-shaped in others, reflecting variations in the rate of subduction, the composition of the descending plate, and the amount of sediment that has accumulated on the trench floor. But even the most recent surveys have mapped only a fraction of the trench's total length. The Philippine Trench stretches for more than 1,300 kilometers. The total area of its floor that has been mapped to high resolution is a small percentage of the whole. The rest remains, in cartographic terms, a blank space. For most of human history, the depth of the ocean off the eastern Philippines was unknown and unknowable. Filipino fishermen, whose ancestors have fished these waters for thousands of years, knew that the water offshore was deep. They knew that certain areas were favored by deep water species, by the large tuna and marlin that migrate through the western Pacific. They knew that the currents could be treacherous and that typhoons could arise with terrifying speed. But the concept of a trench, a narrow, steep-walled chasm reaching more than 10 kilometers beneath the surface, was beyond the scope of pre-industrial knowledge. The Philippine Trench was hidden by the same opacity that hides all deep ocean features, the impenetrability of seawater to light, to radar, to the unaided human senses. The ocean revealed its surface. Its depths it kept to itself. The proximity of the Philippine Trench to land creates conditions unlike those found at any other Hadal Trench on the planet. Consider the gradient. If you set out from the eastern coast of Mindanao in a small boat and travelled east, within approximately 50 to 100 kilometers you would cross from shallow coastal waters, warm and sunlit and teeming with coral reef life, to waters overlying a trench more than 10,000 meters deep. In that short horizontal distance, the vertical extent of the ocean increases from a few hundred meters to more than 10 kilometers. The seafloor drops away beneath you, with a steepness that has few parallels on land. It is as though the land beside a city suddenly dropped away into a canyon, 10 kilometers deep and 30 kilometers wide, running parallel to the coastward for more than 1,000 kilometers. The people of the eastern Philippines live on the rim of such a canyon every day of their lives. They simply cannot see it. The sediment dynamics of the Philippine Trench reflect this proximity. Rivers draining the mountainous eastern Philippines, islands that receive some of the highest rainfall in Southeast Asia, carry enormous quantities of sediment to the coastal ocean. During typhoons, which strike the Philippines with an average frequency of approximately 20 per year, rainfall and storm surge trigger massive pulses of sediment delivery, landslides that strip hillsides bare, flash floods that scour river channels, and coastal erosion that delivers beach and cliff material directly into the nearshore waters. Some of this material settles on the continental shelf, some is carried by currents along the coast, and some transported by turbidity currents, underwater avalanches of sediment-laden water triggered by earthquakes, or by the sheer weight of accumulated slope deposits, cascades down the steep walls of the trench and reaches the bottom. The hadal floor of the Philippine Trench receives a direct input of terrestrial material that most open ocean trenches do not. The mountains of the Philippines and the floor of the Emden Deep are connected by a continuous chain of gravitational processes that operates every day, every year, in rain and in storm, without interruption, and yet those depths have always been there. Long before the first human settlement appeared on the eastern Philippine coast, the trench was there, dark, deep, pressurized, and alive with organisms that had no concept of the surface world above them, and it will be there long after. The trench operates on geological timescales. Its deepening is measured in fractions of a millimeter per year. Its earthquakes are measured in seconds. Its existence in ages. The human presence on its shores is by comparison a flicker, a brief bright moment on the edge of something incomprehensibly old and incomprehensibly deep. But what forces created this abyss? What is happening right now in the geological machinery beneath the Philippine Trench? And what have scientists found when they have managed, in their rare, brief, expensive visits, to reach the bottom? The answers are more unsettling than anyone expected. The Philippine Trench exists because two pieces of the Earth's outer shell are colliding, and one of them is losing. The collision is slow by human standards, measured in centimeters per year, but it is relentless, continuous, and driven by forces so immense that they reshape the surface of the planet on timescales that reduce human history to an irrelevance. The trench marks the place where the Philippine Sea Plate, a large oceanic plate that underlies much of the Western Pacific, is being forced beneath the Philippine Mobile Belt, a complex assemblage of smaller plates and plate fragments that make up the geological foundation of the Philippine archipelago. This process, subduction, is the same process that creates the Mariana Trench and the Tonga Trench, but in the Philippines, the geological setting is uniquely complex, and the consequences are uniquely dangerous. The rate of subduction at the Philippine Trench varies along its length, but is generally estimated at approximately 6 to 8 centimeters per year. This is faster than the spreading rate of the Mid-Atlantic Ridge, where new oceanic crust is being created at approximately 2.5 centimeters per year, but slower than the extraordinarily rapid convergence at the Tonga Trench, which approaches 24 centimeters per year. The subduction at the Philippine Trench is, by global standards, moderate in speed, but the consequences of even moderate subduction are enormous. The descending Philippine Sea Plate is cold, dense, and old. It sinks into the mantle at angles that vary from relatively shallow in some segments to nearly vertical in others. As it descends, it generates earthquakes, drives volcanic activity, and creates the immense gravitational pull that keeps the trench floor at depths exceeding 10,000 meters. The Philippines sits at the intersection of multiple plate boundaries, making it one of the most tectonically complex regions on Earth. The Philippine Sea Plate is subducting beneath the Philippine Mobile Belt from the east, creating the Philippine Trench. Simultaneously, the Sunda Plate is subducting beneath the Philippine Mobile Belt from the west, creating the Manila Trench along the western coast of Luzon. Between these two subduction zones, the Philippine archipelago is being squeezed, deformed, and uplifted by the converging forces. The result is one of the most seismically active and volcanically active regions on the planet. The Philippines experiences, on average, approximately 20 earthquakes per day, most of them too small to be felt. But several times per decade, major earthquakes of magnitude 7 or above strike the archipelago, causing significant damage and loss of life. This double subduction configuration is unusual on a global scale. Most island arcs are bounded by a subduction zone on one side only. The Philippines is bounded by subduction on both sides, making it a geological vice, compressed between converging plates from east and west. This dual compression creates an extraordinarily complex internal structure. The Philippine Fault Zone, a left lateral strike-slip fault that runs for approximately 1,200 kilometers, through the central Philippines accommodates some of the internal deformation caused by this bilateral compression. The fault is active and has produced destructive earthquakes in historical times. In 1990, a magnitude 7.8 earthquake on the Philippine fault zone struck the island of Luzon, killing more than 1,600 people, destroying buildings, and triggering massive landslides. The fault zone is not directly related to the Philippine Trench, but it is a product of the same tectonic forces. The compression between the two opposing subduction zones, the Philippine Trench to the east and the Manila Trench to the west, generates the internal strain that the fault zone accommodates. The Philippine landscape is not merely sitting above a trench. It is caught between two. The relationship between the Philippine Trench and the seismic hazard facing the Philippines is direct and inescapable. The subduction interface, the zone where the descending Philippine sea plate grinds against the overriding Philippine mobile belt, is a locked fault, a surface along which stress accumulates over decades or centuries until it is released catastrophically in a major earthquake. The megathrust earthquakes that originate on subduction interfaces are among the most powerful seismic events on the planet. The 2011 Tohoku earthquake in Japan, which had a magnitude of 9.0 and generated the devastating tsunami that caused the Fukushima nuclear disaster, was a megathrust earthquake on a subduction interface. The 2004 Indian Ocean earthquake and tsunami, which killed approximately 230,000 people across 14 countries, was a megathrust earthquake on the Sunda subduction zone. The Philippine Trench is capable of producing earthquakes of comparable magnitude, and it gets worse. The proximity of the Philippine Trench to densely populated coastlines means that a major earthquake on the trench's subduction interface could generate a tsunami that would reach the eastern Philippines in minutes, not hours. The warning time available to coastal communities would be measured in tens of minutes at best, and in some locations, much less. The topography of the eastern Philippine coast, with its narrow coastal plains, low-lying fishing villages, and limited evacuation routes, makes the region exceptionally vulnerable to tsunami inundation. The population density of the Philippines, one of the highest in Southeast Asia, compounds the vulnerability. A megathrust earthquake on the Philippine Trench, if it were to occur, could produce a humanitarian catastrophe of enormous proportions. And the geological record suggests that such earthquakes have occurred in the past, though the dating and characterization of these events is still in its early stages. The Manila Trench, on the western side of the Philippines, poses an equally serious tsunami hazard. A megathrust earthquake on the Manila Trench could generate a tsunami that would reach the western coast of Luzon, including the densely populated capital region of Manila, within minutes. The combined tsunami hazard from both the Philippine Trench and the Manila Trench makes the Philippines one of the most tsunami-vulnerable nations on Earth, and the detailed geological and geophysical studies required to quantify these hazards, to map the subduction interfaces, to estimate recurrence intervals, to model potential tsunami scenarios, have been conducted only partially. The science exists. The methods exist. The funding and the sustained institutional commitment required to complete the work do not yet match the scale of the hazard. The geological complexity of the Philippine Trench region extends beyond the trench itself. The subduction process has created a volcanic arc, the chain of volcanoes that runs along the eastern Philippines, parallel to the trench. Mount Mayon, one of the most active volcanoes in the Philippines, with its nearly perfect conical shape and its history of frequent, destructive eruptions, is a product of the subduction process. Magma generated by the descent of the Philippine sea plate rises through the overriding plate and erupts at the surface, building the volcanic edifices that punctuate the Philippine landscape. The Philippines has approximately 24 active volcanoes, and the majority of them owe their existence, directly or indirectly, to the subduction processes occurring at the Philippine Trench and the Manila Trench. In 1991, Mount Pinatubo in the Philippines erupted with a violence that shocked the world. The eruption was the second largest volcanic eruption of the 20th century, exceeded only by the 1912 eruption of Nova Rupta in Alaska. Pinatubo injected approximately 20 million tons of sulfur dioxide into the stratosphere, creating a global aerosol layer that reduced worldwide temperatures by approximately 0.5 degrees Celsius for the following 2 years. The eruption killed approximately 800 people directly and displaced more than 200,000. It destroyed Clark Air Base, a major United States military installation, and reshaped the landscape of central Luzon. Pinatubo was fed by the subduction of the Sunda Plate beneath the Manila Trench on the western side of the Philippines, not the Philippine Trench on the eastern side. But the geological principle is the same. Subduction generates magma. Magma generates volcanoes. Volcanoes generate eruptions. And the Philippines, caught between two subduction zones, lives with the consequences. The biology of the Philippine Trench's Hadol zone is known from a small number of expeditions that have deployed baited landers, free-falling cameras, and sediment traps to the trench floor. The results, while fragmentary, are consistent with what has been found in other Hadol trenches. Amphipods dominate the visible macrofauna. These small scavenging crustaceans arrive at bait packages in swarms, appearing from the darkness within hours, and consuming everything available with a ferocity that testifies to the extreme scarcity of food at those depths. The amphipod communities of the Philippine Trench include species of Herondelia, a genus found in multiple Hadol trenches across the Pacific. Whether the specific populations in the Philippine Trench are genetically distinct from those in the Mariana Trench or the Tonga Trench is a question that remains open, limited by the small number of specimens that have been collected and the difficulty of obtaining genetic material from organisms adapted to extreme pressure. In 2021, a Chinese research team achieved a significant milestone by deploying the Fendaoge, China's deep-sea submersible, to the Philippine Trench. The submersible reached a depth of approximately 10,000 meters, collecting video footage, water samples, and sediment cores from the trench floor. The dive was one of the first crewed missions to the deepest parts of the Philippine Trench, and the data it returned are still being analyzed and published. The footage revealed a seafloor of soft, pale sediment, similar in appearance to the floors of other Hadol trenches, populated by amphipods and other small organisms that scattered in the submersible's lights. The sediment itself contained evidence of the trench's connection to the surface world above, including terrestrial organic matter that had been transported from the Philippine Islands by rivers and gravity flows. The Fendaoge, whose name means striver in Mandarin, is one of only a handful of submersibles in the world capable of reaching full ocean depth. Its pressure hull is a titanium sphere engineered to withstand pressures exceeding 1,000 bars. The sphere is equipped with viewports, cameras, manipulator arms, and sampling equipment, all designed to function at pressures that would destroy most engineering materials. The logistical effort required to deploy the Fendaoge to the Philippine Trench, including the transit of the support vessel across thousands of kilometers of ocean, the calibration of the launch and recovery systems, and the coordination with Philippine authorities for permission to conduct scientific operations in Philippine waters, was enormous, and the result, measured in time on the bottom, was a matter of hours. A few hours at a single location in a trench that stretches for more than 1,300 kilometers. The ratio between what was observed and what remains unobserved is a reminder of how much remains unknown. But here is the problem. A single dive, or even a handful of dives, cannot characterize an ecosystem that stretches for more than 1,300 kilometers. The Philippine Trench is not a single environment. It varies along its length, in depth, in width, in the steepness and composition of its walls, in the amount and type of sediment that accumulates on its floor, in the chemistry of the water that fills it, and in the species that inhabit it. A dive to one location reveals what is present at that location at that moment under those specific conditions. It says nothing about what is present 100 kilometers to the north, or 200 kilometers to the south, or at a different depth along the trench wall, or at a different time of year, when the currents and the food supply may be different. The Philippine Trench is a world. Exploring it with a handful of dives is like exploring a continent with a single photograph taken from a single window. The creatures that inhabit the Philippine Trench have adapted to conditions that would destroy most surface organisms instantaneously. The pressure at the Emden Deep, approximately 1,050 bars, distorts the molecular structure of proteins, the fundamental machines of life. The organisms that survive in the Hadal zone counteract this effect through biochemical adaptations, most notably the accumulation of trimethylamine N-oxide, TMAO, a small molecule that stabilizes protein structure under pressure. TMAO levels in Hadal organisms increase with depth, a pattern observed consistently across multiple species and multiple trenches. The deeper the organism lives, the more TMAO it requires. This is not coincidence, it is molecular necessity. The food supply to the Hadal zone of the Philippine Trench is derived primarily from marine snow, supplemented by the terrestrial organic carbon input that distinguishes this trench from more isolated open ocean trenches. The marine snow that reaches the Hadal floor has been sinking for weeks or months, consumed and reprocessed at every depth. Less than 1% of the organic carbon fixed by photosynthesis at the surface ever reaches the deepest ocean floors. The organisms at the bottom of the Philippine Trench survive on the remnants of remnants, the scraps of a biological feast picked over by every layer of ocean above them. When food arrives, they cannot afford to waste it. When bait packages are lowered by research landers, amphipods arrive in dense swarms within hours, consuming everything with a speed that speaks to the relentless scarcity of their environment. And there is another dimension to the trench's biology that is only beginning to be explored. The steep walls of the Philippine Trench, which descend from the shallow continental shelf to Hadal depths over distances of only a few tens of kilometers, create an extreme gradient of environmental conditions. An organism living on the trench wall at 3,000 meters depth inhabits a fundamentally different world from one living at 8,000 meters, or one living at 10,000 meters. The pressure is different. The temperature is different. The food supply is different. The species composition is different. The trench wall is not a uniform surface. It is a vertical landscape, a cliff face 10 kilometers tall, with its own ecology at every depth. Mapping this vertical ecosystem, documenting how communities change with depth along the trench wall, is a task that has barely been attempted. The technology exists in principle, autonomous underwater vehicles capable of traversing steep terrain at extreme depths, but it has not been deployed to the Philippine Trench in any systematic way. The vertical ecology of the trench wall remains, like so much of the trench itself, a subject of inference rather than observation. But here is what makes this truly terrifying. The Philippine Trench is not merely a scientific curiosity. It is a geological engine that produces earthquakes and feeds volcanoes in one of the most densely populated regions on Earth. More than 100 million people live in the Philippines. Millions of them live on islands directly above or adjacent to the trench. The seismic hazard posed by the trench is real, documented, and insufficiently studied. The volcanic hazard fed by the trench's subduction is real, documented, and continuously active. And the scientific infrastructure dedicated to monitoring and understanding these hazards while it exists is limited by funding, by staffing, and by the extreme difficulty of studying a feature that lies 10 kilometers beneath the surface of the sea. The gap between the hazard and our understanding of it is enormous, and in that gap, more than 100 million people live their daily lives. The seismological record of the Philippine Trench region tells a story of recurring violence. In 1976, a magnitude 7.9 earthquake struck the Moro Gulf, south of Mindanao, generating a tsunami that killed between 5,000 and 8,000 people. The tsunami waves reached heights of up to 9 meters in some locations, inundating villages that had no warning system and no time to evacuate. The earthquake occurred on a fault system associated with the complex tectonic environment of the southern Philippines. It was not directly on the Philippine Trench's main subduction interface, but it demonstrated the devastating potential of seismic activity in the region and the extreme vulnerability of coastal communities. In 2012, a magnitude 6.9 earthquake struck the eastern Visayas, near the northern end of the Philippine Trench, damaging buildings, triggering landslides, and displacing tens of thousands. In 2020, a magnitude 6.6 earthquake struck the southern Philippines, causing casualties and structural damage. These events, while destructive, were not megathrust earthquakes. They were moderate to large events on secondary faults. The megathrust potential of the Philippine Trench's subduction interface, the possibility of a magnitude 8 or greater earthquake rupturing a large segment of the plate boundary, remains the dominant long-term seismic hazard for the eastern Philippines, and the recurrence interval of such events is poorly constrained. The geological forces operating at the Philippine Trench extend far below the trench floor. The descending Philippine sea plate generates a Wadati-Benioff zone, a plane of earthquake foci that traces the slab's descent into the mantle. Beneath the Philippine Trench, this zone extends to depths of approximately 600 kilometers. Deep focus earthquakes, occurring at 300 to 600 kilometers below the surface, are regularly recorded. These deep earthquakes happen because the descending slab remains cold and brittle far below the depth where most rock becomes ductile. The mechanisms by which rock fractures at such extreme pressures include transformational faulting, where mineral phase changes trigger sudden mechanical failure, and dehydration embrittlement, where water released from hydrous minerals reduces effective stress on internal faults. The Wadati-Benioff zone allows seismologists to map the shape of the descending plate, a cold finger of ancient ocean crust reaching hundreds of kilometers into the hot interior of the Earth, carrying with it water, carbon, and the chemical signatures of the surface world. The volcanic arc generated by the Philippine Trench's subduction extends along the eastern Philippine archipelago. Mount Mayon, on Luzon, has erupted more than 50 times in recorded history, producing pyroclastic flows, lahars, and ashfall that have killed hundreds and devastated agricultural land. Its nearly perfect conical shape, considered one of the most symmetrical volcanic cones in the world, is a testament to the regularity and volume of its eruptions. Mount Bulusan, also on Luzon, has produced phreatic eruptions as recently as 2017. Mount Canlaon on the island of Negros erupted in December of 2024, forcing the evacuation of thousands of residents and reminding the nation of the volcanic hazards it faces. Each of these volcanoes owes its existence to the same subduction process that created the Philippine Trench. The magma that feeds them is generated by the descent of the Philippine sea plate, which carries water-saturated minerals into the mantle, lowering the melting point of the overlying rock and triggering the formation of molten material that rises through the crust. The 1991 eruption of Mount Pinatubo, the second largest volcanic eruption of the 20th century, while fed by the Manila Trench's subduction on the western side of the Philippines, demonstrated the catastrophic potential of Philippine volcanism with devastating clarity. Pinatubo injected approximately 20 million tons of sulfur dioxide into the stratosphere, creating a global aerosol layer that reduced worldwide temperatures by approximately 0.5 degrees Celsius for 2 years. The eruption killed approximately 800 people directly and displaced more than 200,000. Pyroclastic flows devastated an area of more than 400 square kilometers. Lahars, torrents of volcanic mud triggered by heavy rainfall on the loose volcanic deposits, continued to cause destruction for years after the eruption, burying towns and reshaping river channels across central Luzon. Pinatubo was not connected to the Philippine Trench. It was fed by subduction at the Manila Trench, but the geological principle is identical. Subduction drives volcanism, and the Philippines, caught between two subduction zones, the Philippine Trench to the east and the Manila Trench to the west, lives with volcanic hazards on both coasts. The islands are not merely between two trenches. They are between two geological furnaces, each capable of producing eruptions that can alter the global atmosphere. The question of biological endemism in the Philippine Trench is among the most important unanswered questions in hadal biology. Each hadal trench functions as a biological island, isolated from neighboring trenches by the shallower waters that separate them. Organisms adapted to pressures exceeding 1,000 bars cannot survive at 600 bars. The kilometers of abyssal plain that separate one trench from the next are, for hadal organisms, as impassable as an ocean separating continents. Over geological time, this isolation may have driven the evolution of unique species in each trench. Testing this hypothesis requires systematic biological sampling from multiple trenches using consistent methods. That work has barely begun in the Philippine Trench. The total number of species formally described from the hadal zone of the Philippine Trench could be counted on two hands. The total number of potential species, the undescribed, the uncollected, the unseen, is almost certainly far larger. The mysteries of the Philippine Trench and its surrounding waters can be understood through 5 distinct phenomena, each one revealing a different facet of the deep ocean's strangeness, each one demonstrating how much remains unknown about a feature that lies within sight of 100 million people. The first phenomenon concerns the extraordinary biodiversity of the waters above the trench. The Philippines sits at the heart of the Coral Triangle, a region of tropical ocean stretching from Indonesia to Papua New Guinea that contains the highest concentration of marine species on Earth. The Coral Triangle covers less than 2% of the global ocean area, but harbours more than 30% of the world's coral reef species, including more than 600 species of reef-building corals, more than 2,000 species of reef fish, and enormous numbers of invertebrates, algae, and marine mammals. The surface waters of the eastern Philippines, directly above the Philippine Trench, are part of this biological hotspot. The contrast between the teeming, sunlit, species-rich waters above and the dark, sparse, pressurized waters 10 kilometers below is one of the most extreme ecological gradients on the planet. This gradient creates a unique situation for the trench's biology. The rich surface waters of the Coral Triangle produce enormous quantities of organic matter through photosynthesis. When organisms in the surface waters die, their remains sink, contributing to the marine snow that feeds the deep ocean below. The Philippine Trench, positioned directly beneath one of the most productive marine ecosystems on Earth, may receive a richer supply of marine snow than trenches located beneath less productive surface waters. This could, in theory, support a denser or more diverse hadal community than is found in open ocean trenches, but the data to test this hypothesis are lacking. The number of biological sampling events in the hadal zone of the Philippine Trench is too small to draw statistically meaningful conclusions about the density or diversity of its organisms relative to other trenches. The Coral Triangle's extraordinary biodiversity is itself a subject of ongoing scientific investigation. Why should this particular region of the tropical ocean harbour so many more species than comparable tropical ocean regions elsewhere? Several hypotheses have been proposed. The centre of accumulation hypothesis suggests that the Coral Triangle acts as a refuge where species from surrounding regions accumulate over time. The centre of origin hypothesis proposes that the region's geological complexity, including its many islands, shallow seas, tectonic collisions, and sea level changes, promote speciation. The centre of overlap hypothesis suggests that the region sits at the intersection of the Indian and Pacific Ocean biogeographic realms, combining species pools from both. Each hypothesis has supporting evidence, and the truth likely involves elements of all three. The geological history of the Coral Triangle is intimately connected to the tectonic processes that created the Philippine Trench. The collision of the Australian, Pacific, and Philippine sea plates has, over tens of millions of years, created a complex mosaic of islands, shallow seas, deep basins, and submerged ridges that provide an enormous variety of habitats within a relatively small geographic area. The rising and falling of sea levels during glacial and interglacial periods has alternately connected and isolated these habitats, creating conditions that promote speciation and the accumulation of diversity. Whilst the Philippine Trench itself is a product of these same tectonic forces, the extraordinary biodiversity of the Coral Triangle and the extreme depth of the Philippine Trench are not coincidences. They are both consequences of the same geological history, the same plate collisions, the same subduction processes that have shaped the Western Pacific for millions of years. but for the Philippine Trench specifically, the relevant implication is this. The biological richness above the trench is extreme. The biological richness below the trench is almost entirely unknown, and the transition between the two occurs over a depth range that no single organism spans. The surface and the deep are connected by gravity, by the sinking of dead matter, by the falling rain of marine snow, but they are separated by pressure, by darkness, by temperature, and by time, the weeks or months it takes for a particle of marine snow to drift from the sunlit surface to the hadal floor. The organisms that thrive in the warm, sunlit, species-rich waters of the Coral Triangle could not survive for a fraction of a second at the bottom of the trench, and the organisms that persist in the crushing darkness of the Emden Deep have never experienced the conditions that exist a few tens of kilometers above them. They inhabit the same ocean, the same body of water, the same continuous fluid medium, and yet they inhabit worlds so fundamentally different that they might as well be on different planets. The gradient between the surface and the deep is not merely biological, it is also acoustic. The sounds of the Coral Triangle's teeming reef ecosystems, the snapping of shrimp, the grinding of parrotfish teeth on coral, the chorus of fish at dawn and dusk, do not penetrate to hadal depths. The sounds that reach the trench floor, if any, are low-frequency geological rumbles, the distant resonance of earthquakes on the subduction interface, the slow creaking of tectonic plates adjusting under immense stress. The acoustic environment changes with depth just as completely as the biological environment does. The noisy, vibrant soundscape of the reef gives way, gradually, to a world of increasingly profound acoustic isolation, until at the bottom of the trench, the only sounds that exist are the ones generated by the trench itself and by the geological processes that created it. The second phenomenon involves the acoustic environment of the Philippine Trench and the creatures that navigate it by sound. The deep waters above and within the trench are traversed by some of the most remarkable sound-producing animals on the planet. Sperm whales, the largest toothed predators on Earth, are present in the Western Pacific and are known to dive to depths exceeding 2,000 meters in pursuit of deep-sea squid. Their echolocation clicks, produced by forcing air through a complex system of chambers and oil-filled organs in their massive heads, can reach volumes of 230 decibels, making them the loudest biological sounds on the planet. These clicks serve two purposes: navigation and hunting. In the total darkness below 1,000 meters, where vision is useless, the sperm whale hunts by sound, sending out clicks and listening for the echoes that return from the bodies of squid in the water ahead. The whale sees with sound. It constructs an acoustic image of the world around it, an image that reveals the size, shape, distance, and movement of its prey in 3 dimensions. And it does this in a darkness so complete that the concept of light has no relevance. Sound behaves differently in water than in air. It travels approximately 4.5 times faster, at roughly 1,500 meters per second, and it can propagate vastly greater distances. Low-frequency sounds, those below approximately 100 Hz, can travel through the deep sound channel, a layer of minimum sound speed at approximately 1,000 meters depth for thousands of kilometers, without significant loss of energy. The deep sound channel acts as a waveguide, trapping sound waves within a horizontal layer and preventing them from dispersing vertically. A sound produced in the deep sound channel on one side of the Pacific can, in principle, be detected on the other side. The deep ocean is not a place of silence. It is a vast acoustic highway carrying biological, geological, and anthropogenic sounds across entire ocean basins. In the waters around the Philippine Trench, the acoustic landscape is shaped by the trench's extreme geology and biology. Earthquakes on the subduction interface produce low-frequency rumbles that propagate through the water and the surrounding seafloor. Volcanic activity along the Philippine volcanic arc contributes submarine rumbles and the hissing of hydrothermal emissions. Ship traffic in the Philippine Sea, one of the most heavily trafficked waterways in the Western Pacific, adds a continuous background of mechanical noise. The thrum of propellers and the low-frequency vibration of engines transmitted through the water column and detectable at great depth. Among the biological sounds, The calls of baleen whales dominate the lowest frequencies. Blue whales produce calls at frequencies as low as 14 Hz, below the range of human hearing. That can travel thousands of kilometers. Fin whales produce their characteristic 20 Hz pulses at regular intervals, detectable across entire ocean basins. Humpback whales produce complex songs that evolve throughout each breeding season. All of these species transit through or reside seasonally in the western Pacific, and their calls form part of the acoustic environment of the Philippine Trench. The trench does not merely contain life, it listens to it. The sounds of the entire ocean converge in its waters, filtered and shaped by the geometry of its walls and the physics of sound transmission in seawater. The waters above the Philippine Trench are also home to the deep-diving beaked whales, members of the family Ziphidae. Cuvier's beaked whale, Ziphius cavarostris, holds the record for the deepest confirmed dive by any mammal, exceeding 2,900 meters. These whales can remain submerged for more than 3 hours. They hunt in the bathypelagic zone, using echolocation to detect and capture deep-sea squid and fish at pressures exceeding 290 bars. Beaked whales are among the least known large mammals on the planet. Some species of beaked whale are known only from a handful of stranded specimens and have never been positively identified alive at sea. They are ghosts of the deep. They surface briefly, breathe, and then vanish, descending into the dark for hours at a time, hunting in a world that no camera has systematically documented. The interactions between deep-diving whales and deep-sea squid in the waters above the Philippine Trench remain among the most poorly documented large animal ecological interactions on Earth. Sperm whales carry the scars of giant squid suckers on their skin, evidence of battles that take place in total darkness at depths exceeding 1,000 meters. The giant squid, Architeuthis dux, reaching lengths of approximately 13 meters, has been confirmed in the western Pacific, but has never been systematically surveyed in the waters above the Philippine Trench. The deep-water squid community of this region, its species composition, its abundance, its depth distribution, its ecological role remains almost entirely unknown. The deep ocean keeps its largest inhabitants hidden. The third phenomenon concerns the peculiar relationship between the Philippine Trench and the typhoons that strike the Philippines with devastating regularity. The Philippines is one of the most typhoon-affected countries on Earth, experiencing an average of approximately 20 tropical cyclones per year, of which approximately 8 or 9 make landfall. Typhoons draw their energy from the warm surface waters of the tropical ocean, and the waters above the Philippine Trench are among the warmest in the Pacific, with sea surface temperatures frequently exceeding 29 degrees Celsius during the typhoon season. The warm water above the trench acts as a fuel source for typhoons, providing the thermal energy that powers the convective processes driving the storm. The physics of this energy transfer is well understood. When warm, moist air rises from the sea surface, the water vapor it carries condenses at altitude, releasing latent heat that drives the storm circulation. The warmer the sea surface, the more moisture the air can carry, and the more latent heat is released during condensation. Sea surface temperatures above approximately 26 degrees Celsius are generally considered the minimum threshold for tropical cyclone development. The waters above the Philippine Trench routinely exceed this threshold by 3 or more degrees during the typhoon season. The trench itself plays no direct role in generating typhoons, but the warm waters above it provide the fuel, and the depth of the trench beneath those warm waters may influence how quickly the fuel is replenished after a storm passes. Typhoon Haiyan, known in the Philippines as Typhoon Yolanda, struck the eastern Philippines in November of 2013 with sustained wind speeds exceeding 300 kilometers per hour, making it one of the most powerful tropical cyclones ever recorded at landfall. The storm crossed the Philippine Sea above and near the Philippine Trench, gaining strength from the warm surface waters before making landfall on the island of Leyte. The storm surge generated by Haiyan reached heights of more than 5 meters in some locations, inundating coastal communities and killing more than 6,300 people. More than 4 million people were displaced. Entire towns were flattened. The city of Tacloban was devastated, its coastal areas swept clean by a wall of water driven ashore by the storm's extreme winds. Haiyan was not caused by the Philippine Trench, but the warm surface waters above the trench provided the energy that made the storm so destructive. And the depth of the water column above the trench may have played a subtle but significant role. When a typhoon passes over shallow water, the strong winds mix the surface layer with the cooler water below, reducing sea surface temperatures and cutting off the storm's energy supply. This negative feedback limits the intensity of storms that cross shallow continental shelves. But when a typhoon passes over deep water, such as the waters above the Philippine Trench, the warm surface layer is underlain by a much deeper column of water, and the mixing induced by the storm may not be sufficient to bring cold deep water to the surface. The warm layer persists, the energy supply is maintained, the storm continues to strengthen or maintains its intensity longer than it would over shallower waters. This relationship between deep water and typhoon intensity is an area of active research. Some studies have suggested that the depth of the warm water layer, the layer of water above 26 degrees Celsius, is a better predictor of typhoon intensity than sea surface temperature alone. A shallow warm layer will cool quickly when mixed by a storm. A deep warm layer will resist cooling and continue to supply energy. The Philippine Trench, with its extreme depth, underlies a region where the warm layer can extend to considerable depth during the typhoon season, potentially providing a sustained source of energy for storms that cross the Philippine Sea. The connection between the trench and the typhoons that devastate the Philippines is not direct. It is mediated by oceanography, by the depth and temperature structure of the water column, by the dynamics of ocean mixing, and by the atmospheric processes that convert warm moist air into the rotational energy of a tropical cyclone. But the connection exists, and understanding it requires understanding not just the surface of the ocean, but its depth, its thermal structure, and the physics of heat transport between the deep and the shallow. Typhoon Haiyan also had a measurable effect on the deep ocean itself. Research has shown that the passage of powerful typhoons can generate internal waves, oscillations that propagate along the density boundaries within the ocean's water column, carrying energy downward from the surface to considerable depth. The extreme winds and pressure changes associated with a Category 5 typhoon, like Haiyan, generate internal waves that can penetrate to depths of several hundred meters or more, potentially influencing the mixing and circulation of deep waters. Whether these internal waves penetrate to Hadal depths in the Philippine Trench is unknown. But the question is worth asking. The surface and the deep are not separate worlds. They are connected by physics, by gravity, by pressure, by the continuous transmission of energy from the atmosphere through the water column to the seafloor. The typhoons that devastate the Philippine coast may, in ways that we have not yet measured, send their influence all the way to the bottom. The fourth phenomenon involves the deep-sea organisms that exhibit adaptations so extreme that they challenge conventional understanding of biological possibility. The Hadal zone of the Philippine Trench, like that of other deep trenches, is home to organisms whose bodies have been reshaped by pressure, darkness, and scarcity in ways that would be unrecognizable to a surface biologist. Consider the Hadal snailfish, documented in several Pacific trenches at depths exceeding 8,000 meters. These fish are pale, translucent creatures with gelatinous bodies, poorly mineralized bones, and no swim bladder, the gas-filled organ that most fish use to control buoyancy. At Hadal pressures, a swim bladder would be compressed to a fraction of its original volume and would provide no useful buoyancy control. The snailfish has dispensed with it entirely, maintaining neutral buoyancy through the watery composition of its tissues. Its body is so soft that it can barely maintain its shape when brought to the surface. At depth, the surrounding pressure supports its body from every direction. At the surface, without that pressure, the fish collapses. It is a creature that literally cannot exist outside its own extreme environment. The pressure that would kill a surface fish is the pressure that holds the snailfish together. Consider the anglerfish, one of the most iconic creatures of the deep ocean. The female anglerfish possesses a bioluminescent lure a modified dorsal fin spine tipped with a glowing bulb, which she dangles in front of her enormous mouth to attract prey in total darkness. But the anglerfish's most extreme adaptation is reproductive. In many species, the males are dramatically smaller than the females. Upon finding a female, a male bites into her skin and fuses permanently with her body. His circulatory system merges with hers, his organs degenerate. He becomes, in biological terms, a permanently attached reproductive organ. This extreme sexual parasitism is a direct response to the near impossibility of finding a mate in the vast, featureless darkness of the deep ocean. When encounters between individuals may be separated by vast distances and long periods, the male holds on once he finds her. He merges, he becomes part of her. In the deep ocean, the pressure to find a mate is as relentless as the pressure of the water itself. Consider the black swallower, a small bathypelagic fish that can consume prey more than twice its own length and 10 times its own mass. Its hinged jaw and distensible stomach allow it to engulf enormous meals, after which it drifts through the darkness with the outline of its prey visible through its stretched, nearly transparent belly. This adaptation is a rational response to the extreme scarcity of food. In the deep, when food arrives, you consume it entirely. The next meal may not come for weeks or months. Consider the giant isopod, Bathynomus giganteus, and its relatives, crustaceans related to the common woodlouse that can reach lengths of up to 76 centimeters in the deep ocean, nearly 3/4 of a meter, compared to the 1 or 2 centimeters typical of their terrestrial relatives. This phenomenon, deep-sea gigantism, is observed in multiple groups of deep ocean organisms. Its causes are debated, with hypotheses including higher dissolved oxygen at low temperatures, the absence of visual predators, and metabolic advantages of larger body size in an environment of extreme food scarcity. The deep ocean grows its organisms large. The familiar becomes alien. The rules of surface biology bend and break under conditions that have no surface equivalent. The biochemistry of hadal organisms reveals adaptations at the molecular level that are as remarkable as the anatomical adaptations visible to the eye. The proteins of hadal organisms are loaded with TMAO, the pressure counteracting solute that prevents pressure from distorting protein structure. The cell membranes of hadal organisms are enriched in unsaturated fatty acids, which maintain membrane fluidity at the near freezing temperatures and extreme pressures of the hadal zone. Every level of organization in a hadal organism, from its proteins to its membranes to its bones to its body plan, has been shaped by the specific demands of its environment. These are not surface organisms that have wandered into the deep. These are organisms sculpted by the deep, from the molecular level upward, over spans of time that dwarf human history. The deep waters above the Philippine Trench also harbour a phenomenon that, when first discovered, was mistaken for the ocean floor itself. The deep scattering layer is a dense horizontal band of organisms, primarily small fish, squid, shrimp, and jellyfish, that resides in the mesopelagic and upper bathypelagic zones during the day and rises toward the surface at night to feed. This layer is so dense and so acoustically reflective that early sonar operators during the Second World War detected it as a false bottom, a phantom seafloor at 300 to 500 meters depth that seemed to rise and fall with the sun. It took years for scientists to determine that the false bottom was biological, not geological, a living layer of organisms so concentrated that it reflected sonar as effectively as rock. The deep scattering layer above the Philippine Trench is part of this global phenomenon. The daily vertical migration of this layer, the diel vertical migration, involves billions of tons of biomass rising and falling through the water column every 24 hours, making it the largest daily movement of living matter on the planet. And it happens every day, silently, invisibly, in the waters directly above the third deepest place on Earth. Consider the vampire squid, Vampiroteuthis infernalis, an organism whose Latin name translates to vampire squid from hell. Despite its fearsome name, the vampire squid is not a predator. It feeds on marine snow, the drifting particles of dead organic matter, capturing them with 2 specialized filaments coated in sticky mucus. It lives in the oxygen minimum zone at depths of 600 to 1,200 meters. in water where dissolved oxygen levels are so low that most organisms cannot survive. The vampire squid has the lowest mass-specific metabolic rate of any cephalopod. It barely moves, it conserves energy with an efficiency that borders on suspended animation. Its eyes are enormous relative to its body, among the largest in the animal kingdom, adapted to detect the faintest bioluminescent flashes in the darkness. And when threatened, it inverts its webbed arms, turning itself inside out to expose a display of bioluminescent photophores and fleshy spines that startle predators. The vampire squid is not a creature of the hadal zone. It lives thousands of meters above the trench floor, but it is part of the ecosystem that exists above the Philippine Trench, part of the vertical continuum of life that extends from the sunlit surface to the crushing darkness of the Emden Deep. Recent research has also revealed the presence of microbial life deep within the sediments of hadal trenches, including communities that persist centimeters and even meters below the seafloor in layers of compressed mud that have been accumulating for geological ages. These subsea floor microbes are among the most extreme forms of life on Earth. They exist in near total darkness, under extreme pressure, at near freezing temperatures, with energy supplies so limited that individual cell divisions may take decades or centuries. They subsist on the chemical energy available in the sediment itself, the slow breakdown of organic compounds, the reactions between minerals and water, gradients so faint they barely register on instruments. Some estimates suggest that the total biomass of subsea floor microbes across the entire global ocean may rival or exceed the total biomass of all life on the surface. If this is correct, then the majority of life on Earth, by mass, is not in the forests or the oceans or the cities. It is in the mud, in the sediment, beneath the seafloor, in the dark. The hadal zone of the Philippine Trench, with its thick accumulation of sediment from both marine and terrestrial sources, may harbour particularly rich subsea floor microbial communities, but their composition, their diversity, and their metabolic capabilities remain almost entirely unknown. The fifth phenomenon returns us to the question that haunts all discussions of the deep ocean: contamination. Persistent organic pollutants, including polychlorinated biphenyls and polybrominated diphenyl ethers, have been detected in the tissues of amphipods and other organisms collected from hadal trenches across the Pacific. The Philippine Trench, with its proximity to a densely populated and rapidly industrializing nation, may be particularly vulnerable to contamination. The rivers of the eastern Philippines carry industrial effluent, agricultural runoff, plastic waste, and other contaminants into the coastal ocean. Some of this material is transported to the trench by currents, by gravity flows, by the sinking of contaminated organic matter. The trench acts as a sink, a place where surface-derived material accumulates in sediment that may not be disturbed for geological ages. In 2019, researchers documented the presence of microplastic contamination in sediment samples from multiple hadal trenches, including locations in the Western Pacific. The concentrations found were, in some cases, higher than those found in some of the most polluted surface waters. The deepest places on Earth are not pristine. They are contaminated with the debris of human civilization. Plastic bags, microplastic particles, industrial chemicals banned decades ago, these have all been documented at hadal depths. And the Philippine Trench, closer to a major source of terrestrial pollution than any other hadal trench on Earth, may be receiving a disproportionately large share of this contamination. The numbers are striking. The Philippines is estimated to be among the top contributors to oceanic plastic pollution globally. The country's rapidly growing population, which exceeds 110 million, its limited waste management infrastructure in many coastal and rural areas, and its extensive coastline of approximately 36,000 kilometers create conditions that promote the transfer of plastic waste from land to sea. The Philippines generates an estimated 2.7 million tons of plastic waste per year, of which a significant fraction enters the marine environment through rivers, coastal dumping, and storm-driven runoff. Some of this plastic floats and is carried by currents to accumulate in the great oceanic garbage patches. Some sinks, weighted by fouling organisms and sediment. Some is broken down by sunlight and wave action into microplastic fragments that are carried by currents to every corner of the ocean, and some, inevitably, finds its way to the trench, carried by turbidity currents down the steep walls, incorporated into the sinking rain of marine snow, or transported by deep water currents. Plastic from the surface world reaches the bottom of the Emden Deep, more than 10 kilometers below. The deepest, most inaccessible part of the Philippine marine environment is being contaminated by the same waste that washes up on the beaches of Manila Bay and the shores of Boracay. The irony is inescapable. The most remote habitat in the Philippine marine realm is being polluted by the same communities that live closest to it. The pollution precedes the science. The contamination precedes the understanding. And the organisms that bear the burden of this pollution are species that most Filipinos will never know exist, living in an environment that most Filipinos will never see. Each of these 5 phenomena, the extraordinary surface biodiversity that exists directly above the trench, the acoustic world of deep-diving whales and hidden squid, the connection between the trench's warm waters and the typhoons that devastate the Philippines, the extreme biological adaptations of hadal organisms, and the contamination that has already reached the trench floor, represents a different facet of the same underlying reality. The Philippine Trench is not known to us. It is not mapped. It is not catalogued. It is not understood. It is the 3rd deepest place on Earth. It lies within sight of one of the most densely populated nations in the world. And it is, by every available measure, among the least explored features on the surface of the planet. There is a fact about the deep ocean that, once heard, cannot be comfortably forgotten. Approximately 95% of the Earth's ocean floor has never been directly observed by human beings. Not mapped in detail, not photographed, not sampled, not visited by any camera, any submersible, any instrument. The Philippine Trench lies within that vast, unobserved 95%. Its general shape is known from satellite-derived gravity data, which infers seafloor topography from subtle variations in the height of the sea surface. But the resolution of this data is measured in kilometers. The detailed features of the trench, the individual faults, the sediment accumulations, the biological habitats, the potential mineral deposits, the geological structures that determine where and how earthquakes occur, none of these can be resolved from orbit. They require ship-based multi-beam sonar deployed from research vessels, passing slowly back and forth above the trench. And that survey work has been conducted for only a small fraction of the trench's total length. Let that sink in. The 3rd deepest place on Earth, a feature more than 1,300 kilometers long, lying within 100 kilometers of a nation of more than 100 million people, and the majority of its floor has never been seen in any meaningful detail. The reasons are familiar. The deep ocean is expensive to explore. It is logistically challenging. It is physically dangerous. It is technologically demanding. The instruments required to operate at 1,000 bars must be engineered to standards that exceed those of most aerospace applications. The submersibles capable of reaching hadal depths are rare, expensive, and in constant demand. The research vessels required to support deep-sea operations are few in number and costly to operate. And the Philippine Trench, despite its proximity to land, is located in a region that presents its own logistical challenges. The typhoon season limits the window for safe operations. The political and bureaucratic requirements for conducting scientific research in Philippine waters add complexity to expedition planning. The nearest major deep-sea research infrastructure is located in Japan, China, and Australia, each thousands of kilometers from the trench. The comparison between deep ocean exploration and space exploration is instructive and, when examined in detail, deeply disorienting. A spacecraft must protect its occupants from a pressure differential of 1 bar, the difference between 1 atmosphere inside the craft and vacuum outside. The engineering is well understood. A deep-sea submersible at the bottom of the Philippine Trench must protect occupants from a pressure differential of more than 1,000 bars. The engineering challenge is not merely greater, it is qualitatively different. The titanium pressure sphere of a full ocean depth submersible must be machined to tolerances measured in fractions of a millimeter. Any imperfection, any microscopic flaw in the crystal structure of the metal can become a point of catastrophic failure at 1,000 bars. The viewport must be optically clear and structurally capable of withstanding pressures that would implode most engineering materials. The seals, the cable penetrations, the hatches, every point where the hull is breached is a potential failure point. At 1,000 bars, failure is not a slow leak, it is instantaneous and total. In space, radio signals travel at the speed of light, enabling real-time communication with spacecraft hundreds of thousands of kilometers away. In water, radio is absorbed within meters. Communication at Hadal depths relies on acoustic signals, sound waves that travel through the water at roughly 1,500 meters per second. Acoustic communication is slow, low bandwidth, and unreliable in the complex geometry of a deep trench. A pilot at the bottom of the Philippine Trench can send simple messages to the surface. High-definition video, the kind of rich data stream that enables real-time decision-making, is beyond the capability of acoustic links. In space, a spacecraft can deploy solar panels and harvest energy for as long as the panels function. In the deep ocean, a submersible carries batteries. When the batteries are depleted, the mission ends. There is no way to extend the dive. There is no way to recharge. Every hour on the bottom is an hour closer to the moment when the pilot must descend. The deep ocean does not grant extensions. The Nippon Foundation and the General Bathymetric Chart of the Oceans launched the Seabed 2030 project with the goal of mapping the entire ocean floor to modern standards. As of the most recent assessment, approximately 25% of the ocean floor had been mapped. The remaining 75%, an area vastly larger than all the continents combined, remains unmapped at the resolution needed for scientific study. The Philippine Trench lies within this unmapped majority. Its general outline is known from satellite-derived gravity data, but the detailed features, the individual faults and ridges that determine where earthquakes occur, the sediment deposits that harbour Hadal communities, the potential chemosynthetic sites on the forearc, none of these can be resolved from orbit. They require ship-based multi-beam sonar surveys, slow, methodical, expensive, and constrained by weather and logistics. Mapping the entire Philippine Trench to high resolution would require hundreds of ship days of dedicated survey time. That survey has not been funded or conducted. The disparity between our mapping of the deep ocean and our mapping of other worlds is not merely striking. It is, when examined closely, disorienting. We have mapped the surface of Mars to a resolution of approximately 100 meters per pixel using orbital cameras. We have mapped the gravitational field of the Moon in enough detail to detect density variations beneath its surface. We have measured the chemical composition of the atmospheres of planets orbiting distant stars by analyzing the spectra of starlight. And we have not mapped the Philippine Trench, a feature on our own planet, in enough detail to identify the individual faults that produce earthquakes capable of generating devastating tsunamis. The surface of Mars has been photographed at higher resolution than the floor of the third deepest trench on Earth. Mars is airless, waterless, and, as far as we know, lifeless. The Philippine Trench is filled with water, home to life forms we have not described, and situated above a seismic hazard that threatens more than 100 million people. The allocation of scientific attention is not proportional to the significance of the subject. It is proportional to the aesthetics of the environment and the political prestige of the exploration. Space is dramatic, the deep ocean is not, and so the deep ocean is neglected. The question of long-term monitoring is arguably the most critical gap in our knowledge of the Philippine Trench. At present, there are no permanent monitoring stations on the trench floor, no autonomous sensors continuously measuring temperature, pressure, chemistry, or biological activity at Hadal depth, no bottom-mounted seismometers recording the micro-earthquakes and strain events that mark the slow accumulation of stress along the subduction interface. Every piece of data from the Philippine Trench has been collected during brief, expensive expeditions separated by years of absence. We have snapshots, we do not have a time series. We have data points, we do not have trends, we have isolated observations. We do not have the continuous record needed to detect changes, to identify patterns, or to forecast hazards with any meaningful precision. The technology to establish permanent monitoring stations at Haddle depths exists, in principle. Ocean bottom seismometers can be deployed to depths of several thousand meters and have been used extensively in other subduction zone settings. Autonomous sensors capable of measuring temperature, conductivity, and pressure are commercially available and have been deployed at abyssal depths in various ocean basins. The challenge is not technological, it is logistical and financial. Deploying and maintaining instruments at Haddle depths in a remote region subject to severe weather requires sustained institutional commitment and sustained funding. Individual research grants, typically lasting 3 to 5 years, are insufficient to establish the kind of long-term monitoring network that the seismic and biological hazards of the Philippine Trench demand. What is needed is a commitment measured in decades, not grant cycles, a commitment to understanding a feature that has been there for millions of years and will continue to produce hazards for millions more. This is not science fiction. This is the factual condition of deep ocean exploration technology in the 21st century. The third deepest place on Earth lies within sight of one of the most populated nations in the world, and the technology required to visit it safely is among the most demanding ever developed. The disparity between what we know about the Philippine Trench and what we need to know is not merely academic. It has practical consequences that affect millions of people. The seismic hazard posed by the trench is real and poorly quantified. The subduction interface beneath the eastern Philippines is a potential source of megathrust earthquakes, events that could generate tsunamis capable of reaching coastal communities within minutes. Understanding the geometry of the plate interface, the distribution of locked and creeping segments along the subduction zone, the recurrence intervals of past earthquakes, and the likely magnitude and location of future events requires detailed geological mapping of the trench floor and the adjacent sea floor. That mapping has not been done. The seismic hazard assessment for the eastern Philippines is based on incomplete data, extrapolations from better studied subduction zones elsewhere, and the limited instrumental record of earthquakes in the region. Something is wrong with our assumptions about what constitutes adequate knowledge of a geological hazard. We live above a trench that can produce earthquakes capable of killing tens of thousands of people. We have not mapped that trench in sufficient detail to understand the structure of the fault that produces those earthquakes. We have not installed permanent monitoring stations on the trench floor to record the slow accumulation of strain that precedes major seismic events. We have not conducted the systematic geological surveys required to estimate the recurrence intervals of past megathrust earthquakes. We are living above a loaded weapon, and we have not bothered to examine its mechanism. The comparison with the Moon is instructive. 12 human beings walked on the lunar surface during the Apollo program. The Moon is approximately 384,000 kilometers from Earth. The Emden Deep is approximately 10.5 kilometers below the surface of the Philippine Sea. The bottom of the Philippine Trench is roughly 36,000 times closer than the Moon, and yet fewer people have reached it. The Moon has been mapped to a resolution of meters using orbital laser altimeters. The Philippine Trench has been mapped at a resolution of kilometers using satellite-derived gravity. The Moon has been sampled by multiple missions that returned hundreds of kilograms of rock and soil to Earth. The Philippine Trench has been sampled by a handful of expeditions that returned a few kilograms of sediment and a few jars of preserved organisms. The Moon is airless, waterless, and lifeless. The Philippine Trench is filled with water, teeming with life, and sitting atop one of the most powerful earthquake-generating fault systems on Earth. And yet, the Moon receives more scientific attention, more funding, more public interest, and more political support than the third deepest place on our own planet. Let that sink in. The biological stakes are also significant. The Philippine Trench harbours a hadal ecosystem that is almost entirely undescribed. The species that inhabit it may be unique to this trench, found nowhere else on Earth. The ecological relationships between those species, the food web that sustains them, the biochemical adaptations that allow them to survive at 1,000 bars, all of these are subjects of near total ignorance. If these species are unique, then their loss, through contamination, through ecosystem disruption, through changes in the food supply, driven by surface-level alterations in ocean productivity, would be irreversible. We cannot protect what we do not know exists. The pharmaceutical and biotechnological potential of hadal organisms adds another dimension of urgency. The enzymes, proteins, and metabolic compounds produced by organisms adapted to extreme pressure and near-freezing temperatures represent a molecular library that has been refined by natural selection under conditions that surface laboratories cannot replicate. Some deep-sea compounds have already shown promise in antibiotic and anti-cancer research. The biochemical library at the bottom of the Philippine Trench has never been systematically sampled. We do not know what compounds are there. We do not know what applications they might have. We know only that extremity drives biochemical novelty, and that we have barely looked. The connection to astrobiology is also relevant. If chemosynthetic communities exist on the Philippine Trench forearc, as they do in the Mariana Trench system, they would represent ecosystems powered by the Earth's internal chemistry rather than sunlight. Such ecosystems are our best analogues for the environments that may exist on Europa, Jupiter's ice-covered moon, and Enceladus, Saturn's small moon with its water vapor plumes and evidence of hydrothermal activity. Studying the chemosynthetic potential of the Philippine Trench is not merely an exercise in understanding our own planet. It is preparation for understanding what we might find when we send probes to explore the dark oceans of other worlds. The contamination question adds urgency to all of this. The Philippine Trench, with its proximity to a densely populated and rapidly industrializing nation, may be particularly vulnerable to contamination. The rivers of the eastern Philippines carry industrial effluent, agricultural runoff, plastic waste, and other contaminants into the coastal ocean. Some of this material is transported to the trench by currents, by gravity flows, by the sinking of contaminated organic matter. The trench acts as a geological sink, a place where surface-derived material accumulates in sediment that may not be disturbed for geological ages. Persistent organic pollutants, including polychlorinated biphenyls and polybrominated diphenyl ethers, have been detected in the tissues of amphipods and other organisms collected from hadal trenches across the Pacific. PCBs, industrial chemicals banned in many countries in the late 1970s and early 1980s, have travelled through pathways that we do not fully understand to reach the most remote habitats on the planet. They have been incorporated into the tissues of organisms that have never been within thousands of kilometers of an industrial facility. The concentrations found in some hadal amphipods have been comparable to those found in crustaceans living in heavily polluted coastal estuaries. The deepest places on Earth are not pristine. They are contaminated. The biological effects of these contaminants on hadal organisms are almost entirely unknown. On the surface, PCBs are known to disrupt endocrine function, impair reproductive success, and compromise immune systems in a wide range of organisms. Whether similar effects occur in hadal amphipods and other deep-sea organisms is a question that has barely been addressed. The metabolism of hadal organisms is slow. Their reproductive rates are low. Their populations may be small and isolated. If contaminants impair the reproductive success of hadal species, the populations may not recover. The combination of small population size, slow reproduction, limited gene flow between isolated trench populations, and chronic exposure to persistent organic pollutants creates conditions that could, in theory, drive hadal species toward extinction before they have been formally described by science. We could lose species that we have never named to contamination that we delivered to their habitat through processes we do not and fully understand. That is not a hypothetical scenario. It is a plausible consequence of the current trajectory. In 2019, researchers documented the presence of microplastic contamination in sediment samples from multiple hadal trenches, including locations in the Western Pacific. The concentrations found were, in some cases, higher than those found in some of the most polluted surface waters. Microplastics, fragments smaller than 5 millimeters, derived from the breakdown of larger plastic items, are now ubiquitous in the marine environment. They have been found in Antarctic sea ice, in Arctic snow, in the deepest sediments of the Mariana Trench and in the tissues of organisms from every ocean depth zone. The Philippine Trench, closer to a major source of terrestrial pollution than any other Hadal Trench, may be receiving a disproportionately large input of microplastic contamination. The numbers are striking. The Philippines is estimated to be among the top contributors to oceanic plastic pollution globally. The country's rapidly growing population, which exceeds 110 million, its limited waste management infrastructure in many coastal and rural areas, and its extensive coastline of approximately 36,000 kilometers create conditions that promote the transfer of plastic waste from land to sea. The Philippines generates an estimated 2.7 million tons of plastic waste per year, of which a significant fraction is estimated to enter the marine environment. Some of this plastic floats, some sinks. Some is broken down by sunlight and wave action into microplastic fragments that are carried by currents throughout the ocean, and some inevitably finds its way to the trench. The deepest, most inaccessible part of the Philippine marine environment is being contaminated by the same waste that washes up on the beaches of Manila Bay and the shores of Boracay. The mechanisms of contaminant transport to Hadal depths are complex and not fully understood. Some pollutants arrive via the sinking of dead organisms that ingested contaminated food near the surface. A fish that consumes microplastic-laden plankton in the sunlit zone dies, sinks, and is consumed by a mesopelagic scavenger, which dies and sinks further, and so on, in a cascading transfer of contamination through the vertical food chain. Some pollutants are transported by deep water currents that carry contaminated water masses from industrialized coastal regions into the open ocean and ultimately into the trench. Some are delivered by turbidity currents, the underwater avalanches that carry surface-derived sediment down the steep walls of the trench to the bottom. And some may arrive through the atmospheric deposition of pollutants, which fall on the sea surface and are then incorporated into the sinking flux of marine snow. Each of these pathways contributes to the accumulation of contaminants at Hadal depths, but the relative importance of each, the rates of delivery, and the long-term consequences for Hadal organisms are all subjects of active research with limited data. The irony is the same irony that haunts every deep ocean contamination story. Our pollution arrives before our instruments. Our waste reaches the trench floor before our cameras do. We are contaminating an ecosystem that we have not catalogued, altering a community that we have not described, and introducing chemicals into an environment whose baseline chemistry we have never measured. We are conducting an experiment in contamination, blindly, without controls, without monitoring, and without the ability to undo what we have already done. The deeper truth about the Philippine Trench is that it is not merely deep. It is not merely dark or cold or pressurized or seismically active or biologically unknown. It is all of these things. And it is all of these things in the shadow of one of the most densely populated nations on Earth. The Mariana Trench is remote. The Tonga Trench is in the middle of the Pacific. The Philippine Trench is right there, just offshore. Close enough to see the mountains of Mindanao from its western rim. Close enough that the rivers of the eastern Philippines carry their sediment and their pollutants directly to its edge. Close enough that the earthquakes it produces shake the buildings in Davao and General Santos and Tacloban. Close enough that the typhoons that draw energy from the waters above it flatten communities that live within its influence. The Philippine Trench is not a distant abstraction. It is a present, proximate, powerful geological reality that shapes the lives of millions of people who live above it, beside it, and in many ways at its mercy. And here is perhaps the most sobering fact of all. The total amount of time that all human beings in history have spent on the floor of the Philippine Trench is measured in hours, not days, not weeks, hours. The cumulative human presence at the bottom of the third deepest place on Earth, a feature more than 1,300 kilometers long, would not fill a single working shift. We have spent more time waiting in line at a coffee shop than we have spent at the bottom of one of the most significant geological features on our planet. The trench has been there for millions of years. We have visited it for a few hours. And in those few hours, we have glimpsed a world that we are already contaminating, already altering, already affecting, before we have had the chance to understand it. That is not merely a gap in our knowledge, it is a failure of priority, and the consequences of that failure are accumulating, silently, at the bottom of the Philippine Trench, in the tissues of amphipods we have not named, in sediments we have not sampled, in communities we have not described, in a darkness that does not know we exist. What does it mean to live above the Philippine Trench? Not as a hypothetical, not as a thought experiment. What does it mean, in the most immediate and personal sense, to build your home, raise your children, fish for your livelihood, and plan for your future on an island that sits above one of the most powerful subduction zones on Earth? It means living with uncertainty that is not theoretical. The fisherman who sets out from a village on the eastern coast of Mindanao, paddling or motoring into the Philippine Sea to set his nets, is crossing above a trench that descends more than 10 kilometers below his hull. He does not think about the trench. He thinks about the fish, the weather, the current, the price he will get at the market. But the trench is there, beneath him, and the forces operating within it, the slow, relentless accumulation of stress along the subduction interface, the periodic release of that stress in earthquakes, the deep-seated volcanic processes that feed the mountains on the horizon, are shaping his world in ways he cannot perceive. The earthquake that may one day destroy his village will originate in the trench. The tsunami that may one day inundate his coast will be generated by the trench. The typhoon that draws its strength from the warm waters above the trench may strip his roof and flatten his crops. The trench is an invisible but omnipresent force in the life of every person who lives along the eastern Philippine coast, and it operates on timescales that are invisible to the human senses. The stress accumulates for decades, for centuries, and then, in seconds, it is released. The implications for policy and preparation are significant. The Philippines has made substantial investments in disaster preparedness, including tsunami warning systems, earthquake-resistant building codes, and community-based disaster risk reduction programs. But these systems are limited by the same gaps in knowledge that limit our understanding of the trench itself. A tsunami warning system is only as effective as the seismic network that detects the earthquake that generates the tsunami. If the earthquake occurs on a segment of the subduction interface that is not well instrumented, or if the rupture characteristics of the earthquake differ from those assumed in the warning algorithms, the warning may be late, or wrong, or absent entirely. Building codes are only as effective as the seismic hazard maps on which they are based. If those maps underestimate the maximum probable shaking from a Philippine Trench earthquake, then buildings designed to code may still fail. The foundation of disaster preparedness is knowledge, and the knowledge base for the Philippine Trench is, by any objective assessment, inadequate. Consider the implications for biology. The Hadal zone of the Philippine Trench may harbour species found nowhere else on Earth. Every Hadal Trench is a biological island, isolated by its extreme depth from the shallower waters around it. The organisms that have adapted to the specific conditions of the Philippine Trench, its particular pressure, its particular temperature, its particular food supply, its particular chemistry, may represent unique evolutionary lineages. Their biochemistry, shaped by millions of years of adaptation to extreme conditions, may contain molecules of medical or industrial value, enzymes that function at 1000 bars, proteins that remain stable at near-freezing temperatures, metabolic pathways that extract energy from chemicals in ways that surface organisms cannot replicate. These are the raw materials of biotechnology, and they are locked away at the bottom of a trench that we have barely sampled. The pharmaceutical potential of deep-sea organisms is a subject that has attracted increasing attention from researchers and industry. Compounds isolated from deep-sea microbes have shown preliminary promise in antibiotic development, in antiviral research, and in the development of novel enzymes for industrial processes. The deep ocean is, in the language of pharmaceutical research, a chemical library of extraordinary richness, but it is a library that we have barely opened. The Philippine Trenches library remains almost entirely unread. We do not know what compounds are present. We do not know what applications they might have. We know only that the environment is extreme, that extremity drives biochemical innovation and that we have barely looked. Consider what the Philippine Trench reveals about the interconnectedness of Earth systems. The trench is a place where the surface and the deep are linked by flows of material and energy that cross the entire vertical extent of the ocean. Organic matter produced by photosynthesis in the sunlit surface waters sinks as marine snow to the Hadal floor. Terrestrial sediment carried by rivers from the mountains of the Philippines cascades down the trench walls. Pollutants manufactured in factories on land travel through the marine food web and accumulate in the tissues of Hadal amphipods. Earthquakes originating on the subduction interface, more than 10 kilometers below the surface, shake buildings on the islands above. Volcanic magma generated by the descending slab erupts through volcanoes that shape the Philippine landscape. Warm surface waters above the trench fuel typhoons that devastate coastal communities. The trench is a nexus, a point where geological, biological, chemical, and atmospheric processes intersect and interact. Understanding the trench is not merely an exercise in deep-sea science. It is an exercise in understanding how the planet works as a system, how the deep and the shallow, the geological and the biological, the ancient and the immediate, are connected in ways that we are only beginning to appreciate. The deep ocean plays a central role in regulating the planet's climate, and the Philippine Trench is part of that regulatory system. The deep ocean absorbs and stores heat, acting as a thermal buffer that moderates the atmosphere's response to changes in solar radiation and greenhouse gas concentrations. The ocean has absorbed more than 90% of the excess heat generated by human greenhouse gas emissions since the Industrial Revolution. This heat is not distributed evenly. It is concentrated in the upper ocean, but is gradually transported to depth through mixing and circulation processes. The deep waters of the Western Pacific, including those that flow through and around the Philippine Trench, are part of the global thermohaline circulation, the slow, planet-spanning movement of water masses driven by differences in temperature and salinity. Cold, dense water sinks in the polar regions, flows along the ocean floor toward the equator, and rises to the surface in areas of upwelling, completing a cycle that takes roughly 1,000 years. Changes in this circulation, driven by changes in global temperature or ice sheet behavior, can alter climate patterns on a planetary scale. The deep ocean is not separate from the climate system. It is a central, indispensable component of it. The carbon cycle adds another dimension. The subduction process at the Philippine Trench carries sediment, including organic carbon that was originally fixed by photosynthesis at the surface, into the mantle. This subducted carbon is removed from the ocean atmosphere system for geological ages, effectively burying it in the Earth's interior. Some of this carbon is eventually returned to the surface through volcanic outgassing, completing a cycle that operates on timescales of tens of millions of years. The Philippine Trench is one node in this planetary-scale carbon recycling system. Understanding the rates at which carbon is subducted, the efficiency of the trench as a long-term carbon sink, and the geological processes that determine how much carbon is stored versus how much is returned, is relevant not only to geology, but to climate science. The chemosynthetic potential of the Philippine Trench region adds another dimension. The subduction process carries water-saturated minerals into the mantle, and as these minerals are heated and compressed, they release fluids that may rise through the overlying plate and emerge at the seafloor as cold seeps or hydrothermal emissions. If such fluid seeps exist on the Philippine Trench forearc, as they do in the Mariana Trench system, they could support chemosynthetic communities, ecosystems powered by chemical energy from the Earth's interior rather than sunlight. These communities would be of immense interest to astrobiologists who study the potential for life on other worlds. The subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus may harbour conditions similar to those at deep-sea chemosynthetic sites, dark oceans in contact with rocky seafloors, with chemical energy rising from hydrothermal processes. The Philippine Trench and its adjacent environments are analogues for the environments where we might one day search for life beyond Earth. Studying the deep chemosynthetic potential of the Philippine region is not merely academic, It is preparation for one of the most profound questions in all of science: whether life exists elsewhere in the universe. The cultural dimension of the Philippine Trench deserves attention. The Philippine people, and particularly the communities of the eastern Philippines, have lived with the ocean for thousands of years. Their cultures, their economies, their diets, their traditions, and their identities are shaped by the sea. Fishing is not merely an economic activity for coastal Filipino communities. It is a way of life, a cultural practice, a source of identity and pride that has sustained families and communities for generations. The barangay, the basic unit of Filipino community organization, has its etymological roots in the word for boat, a reflection of the maritime heritage that is woven into the fabric of Philippine culture. The waters above the Philippine Trench are among the most productive fishing grounds in the Western Pacific, home to tuna, marlin, mahi-mahi, and dozens of other commercially important species. The livelihoods of millions of Filipino fishers depend on the health and productivity of these waters. The contamination of the trench, the disruption of the deep ocean ecosystems that underlie the surface food web, the geological hazards that threaten coastal communities, these are not abstract concerns for the people of the eastern Philippines. They are immediate, personal, and existential. The fisherman who sets his nets above the trench does not think about hadal amphipods or subduction interfaces. He thinks about providing for his family, but his livelihood is connected through a chain of ecological and geological relationships that spans the full depth of the ocean to the processes occurring at the bottom of the trench and within the descending slab beneath it. The surface and the deep are entangled. The fishing community and the hadal community are part of the same system, and the health of the one depends, in ways that we are only beginning to understand, on the health of the other. Any discussion of the Philippine Trench that fails to account for the human communities above it is incomplete. They are not distant observers, they are participants, they are stakeholders, and they are the people who will bear the consequences, both the costs and the benefits, of whatever we choose to do or fail to do in understanding and protecting the third deepest place on Earth. And consider, finally, the weight of responsibility. The Philippine Trench is not a natural wonder located in a national park, fenced off and protected by rangers. It is an active geological feature embedded in the daily life of a nation. The fish that swim above it feed millions of people. The earthquakes it produces threaten millions more. The pollutants it receives come from the same communities that depend on the ocean for food and livelihood. There is no separation between the trench and the people. They are entangled geographically, economically, and environmentally. And the responsibility of understanding this entanglement, of studying the trench adequately, of monitoring its hazards, of protecting its biology, of mitigating its contamination, falls not only on the Philippines, but on the global scientific community. The Philippine Trench is a global feature. Its earthquakes send waves across the Pacific. Its volcanoes can alter the global atmosphere. Its biology may hold molecules of value to medicine worldwide, and its contamination reflects the waste products of a global economy. The trench belongs to everyone, even as it lies closest to the Philippines. There is a trench in the western Pacific Ocean that stretches for more than 1,300 kilometers along the eastern coast of the Philippines. It is narrow, steep-walled, and deep. So deep that if you stood on its floor and looked upward, you would be looking through a column of water taller than the height at which jetliners cross the sky. You would be standing in total darkness in near-freezing water, under a pressure exceeding 1,000 bars, a force so immense that it reshapes the molecules in every cell of every organism that survives there. You would be standing on a floor of soft sediment that contains, mixed with the ancient shells of foraminifera and the slow rain of marine snow, traces of plastic, of industrial chemicals, of the material footprint of a civilization that has reached this place with its waste before it has reached it with its understanding. This is the Philippine Trench, the third deepest place on Earth. And it is, for all the scientific effort directed at it, for all the crude dives that have descended to its floor, for all the robotic instruments that have sampled its sediment and photographed its inhabitants, one of the most poorly understood geological and biological features on the planet. We began this journey with a question. What lies at the bottom of the Pacific's hidden abyss? The answer, as honest and as incomplete as we can make it, is this. We do not fully know. We know there are amphipods, pale and voracious, swarming over bait in the darkness, with a ferocity that speaks to the unrelenting scarcity of their world. We know there are snailfish, translucent and gelatinous, drifting through water that would crush the strongest military submarine in a fraction of a second. We know there are microbes, living in the sediment, metabolizing at rates so slow that individual cell divisions may span decades. We know there are earthquakes, originating on the subduction interface, capable of generating tsunamis that could reach the Philippine coast in minutes. We know there is contamination, arriving from the surface through pathways we have not fully mapped, accumulating in tissues we have not fully analyzed, with consequences we have not begun to predict. We know these things, and they are a fraction of what there is to know, a thin, incomplete, fragmentary fraction. The Philippine Trench stretches for more than 1,300 kilometers. The total area of its floor that has been directly observed is smaller than a neighborhood. The total time that human beings have spent on its bottom is shorter than a school day. The total number of species described from its hadal zone could be counted on two hands. We have scratched the surface of a place that has no surface at all. There is something both humbling and urgent in this. Humbling because the Philippine Trench reminds us that our maps are incomplete, our catalogues are partial, and our understanding is a small fraction of what this planet actually contains. We live above an abyss, and we do not know what is in it. We walk on the edge of a chasm that descends for 10 kilometers, and we cannot see its bottom. We face a seismic hazard that could reshape our coastlines, and we have not adequately measured its mechanism. The trench humbles us, not through hostility, not through malice, not through any intention at all, for the trench has no intentions, no awareness, no consciousness of our existence. Simply through scale, simply through depth, simply through the quiet, irrefutable fact that it is there, and it is deep, and it is dark, and it is full of things we do not know, and urgent because the trench is not waiting for us to be ready. The stress on the subduction interface is accumulating now, today, at this moment. The pollutants are arriving at the trench floor now, today, carried by the currents and the sinking rain of contaminated organic matter from the surface. The organisms of the hadal zone are being exposed to chemicals they have no evolutionary capacity to metabolize or excrete now, today, in the darkness that we have not illuminated. The trench is not a static exhibit in a museum of geological curiosities. It is an active system, changing, accumulating, releasing, responding to forces from above and below on timescales that range from seconds to geological ages, and our understanding of it is not keeping pace. There is a paradox at the heart of the Philippine Trench that applies to every deep trench on the planet, but is sharpened here by the proximity of human civilization. The trench is simultaneously one of the most violent and one of the most patient places on Earth. It produces earthquakes in fractions of a second that release energy accumulated over centuries. It deepens by fractions of a millimeter over years, but persists for millions. The organisms at its bottom metabolize so slowly that the concept of a generation spans decades, yet they are descended from lineages that stretch back into geological time. The trench exists in two timescales simultaneously, the geological and the seismic, the patient and the catastrophic, and the people who live above it exist in neither. They live in human time, the time of seasons, of years, of lifetimes. They cannot perceive the slow accumulation of tectonic stress. They cannot anticipate the sudden release. They can only endure when it comes and rebuild when it passes. The mismatch between human time and geological time is the fundamental vulnerability of every community that lives above a subduction zone. And the Philippine Trench, with its more than 100 million people living within its influence, represents one of the largest concentrations of human vulnerability to a geological hazard anywhere on the planet. A fisherman in eastern Mindanao who sets out at dawn to cast his nets in the Philippine Sea is crossing above a column of water 10 kilometers deep. Beneath his outrigger, in the darkness far below, amphipods are scavenging on the trench floor, Microbes are metabolizing in the sediment, and the descending slab of the Philippine sea plate is grinding beneath the islands that form his home. He knows none of this. He knows the weather, the currents, the behavior of fish, the rhythm of the tides. He knows which headlands to avoid in rough seas and which channels to follow when the wind changes. He knows his ocean the way his father and his grandfather knew it, through experience and observation and the accumulated wisdom of generations. But he does not know the trench. The trench is below his experience, it is below his observation, it is below his world entirely, and yet it is there, it is always there. And the forces it generates, the earthquakes that shake his village, the tsunamis that threaten his coast, the warm waters that fuel the typhoons that strip his roof, these are part of his life whether he knows their origin or not. The people of the Philippines live above this trench. They live with its earthquakes, they live with its typhoons, they fish in its waters, they swim in its shallows, they build their homes on its rim, and for most of them the trench is invisible. It does not announce itself. It does not signal its presence with any surface expression. The water above it looks the same as the water above the continental shelf. The waves break the same way. The sun reflects the same way. There is no visible boundary, no fence, no warning sign that says, "Here, beneath the warm, blue, inviting surface of the Pacific, the floor drops away for 10 kilometers into a darkness and a pressure that no human body can endure." The boundary between the familiar and the abyss is invisible, and that invisibility is perhaps the most unsettling thing about the Philippine Trench: the crushing weight of water, the eternal darkness, the unexplored depths. These are not merely descriptions of the trench. They are descriptions of the state of our knowledge. We are creatures of the surface. We live in a narrow band of light and air. We have built extraordinary things in that narrow space. Cities and bridges, and telescopes and satellites and computers that can process the light of distant galaxies. But beneath us, separated from us by nothing more than a few hours of sinking through darkness, there is a world that we do not know. A world of pressure, of silence, of strange life, of geological violence, of chemical processes that we have barely begun to measure. The Philippine Trench is one window into that world, and when we look through it, what we see is not the trench itself, but the boundary of what we know. We map the stars, we catalogue the galaxies, we send our instruments to the outer planets and beyond, to the edge of the heliosphere, to the boundary, where the sun's influence gives way to the interstellar medium. And beneath our feet, beneath the warm waters where our children swim and our fishermen cast their nets, beneath the shipping lanes, and the typhoon tracks and the surface that we cross and recross every day, there is a place 10 kilometers deep that we have visited for fewer hours than we spend sleeping in a single night. The Philippine Trench is not the most important feature on this planet, but it may be the most important feature we have chosen not to study. And in that choice, in that sustained institutional civilizational decision to look up rather than down, to fund the distant rather than the proximate, to explore the photogenic rather than the dark, there is a lesson about priorities that the next earthquake, the next tsunami, the next discovery of contamination at Haddle depth may eventually force us to learn. The darkness holds more than we know. It has been holding it for longer than we can comprehend. Beneath the warm waters of the Philippine Sea, beneath the fishing grounds and the shipping lanes and the typhoon tracks, beneath 10 kilometers of black, silent, crushing ocean, the trench endures. It does not change because we have noticed it. It does not reveal itself because we have sent a submersible to its floor for a few hours and then departed. It continues, patient, deep, dark, full of life we have not named, producing sounds we have not yet recorded, harbouring chemistry we have not analysed, accumulating our waste with an indifference that should give us pause. The Philippine Trench is not waiting for us. It is simply there, and in its depth, in its darkness, in its patient, ancient, relentless presence, there is a truth that the surface world would do well to remember. The planet is deeper than we know. The ocean is vaster than we have explored, and what lies beneath is not empty. It is full of pressure, full of silence, full of life, full of questions that we have not yet learned to ask, let alone answer. And it is patient, very, very patient. and it will be there long after we are gone.